last night's problems.
There was one where it was like, we don't know how to take the derivative, and it was like literally the same thing set of an integral. How am I supposed to realize that I don't know how to do it and not try to do it? You know what I mean?
Let's see, where was that? Okay, yeah, this one, right?
Yeah, so how am I supposed to know to like not try that? Because
So,
because I thought I knew we knew how to do it, and I started to do it.
How many?
so this is the same as this, right?
Yeah.
For us to be able to take the antiderivative of this, we would have to use some kind of chain rule, right? I mean, to take the derivative of this, we would have something multiplied out here, right? The derivative of the inside. So in order to take the antiderivative, we would have to have something like that. We would have to think about this as a potential U substitution problem, where we would have some function multiplied by its derivative. So we don't know how to take that antiderivative by hand. I'm guessing this one may have been a tempting choice.
Wait, what was the answer? E?
The answer is E, yes.
I guess I did not.
Good job.
I definitely just thought I understood it better.
So, I mean,
Yeah, that's the right answer. You're like, yeah.
Yeah. So why do you think you don't understand it if you've got the right answer?
Because I'm not gonna do it. I'm not gonna realize that like, oh, I don't know how to do this. I'm gonna pick B.
The most complex answer choice isn't always the right choice. I mean, this is literally just the antiderivative. Yeah. So. But yeah, I mean, this is something that we will not learn how to do by hand. Bless you. That's a Calc 2 idea, to do that by hand. So I mean, just kind of looking at this, if you've got 3 choices that are involve integrals and only 2 that are actual functions, odds are it's going to be one of the integral ones. So I mean, just kind of using test-taking strategies like that, like looking at the answer choices, well, a bunch of them are this, it's probably one of those kind of thing.
Right here. I get it. My stupid nails are super.
Any other questions on last night's stuff?
Is the cheese pizza $5 too? What was that mean?
Cheese? I don't know. Alright, let's take a look at applications of integrals then.
This is the part that I want to cry at.
You'll be okay.
We have to push through. I'm so afraid every week. Okay. How much is a cream?
No, I can't with these good because I hadn't tried. That's why.
You can do this.
Okay, mine was the best.
Bro, I feel it. I can try to open my eyes really wide. Like, just to stay here.
Alright, so particle motion. The big ideas that we talked about with integrals, with particle motion, were displacement and total distance. Okay, I probably should have put this on there, but another term for displacement is net distance. For displacement.
I wasn't looking at this.
Okay, so majority of the time, if we are given a particle motion question, we will be given a velocity function. Not always. Okay, sometimes we will be given position, sometimes we would be given an acceleration function, but the majority of the time we will be given a velocity function. To find displacement or total distance, we are taking an integral of our velocity function. Displacement, meaning how far away we are from where we started, is just the integral of velocity. Total distance is the integral of the absolute value of velocity. Okay? Then final position. Okay, if we are asked, here's where we started, here's our velocity function, where am I after 10 seconds? Something like that. Okay, that is wherever we started plus the displacement. Speed is not something that's on the test a lot by itself, okay, but we do need to understand that speed is just the absolute value of velocity, right? Velocity is speed with a direction. Speed is directionless velocity. Now, this idea, whether speed is increasing or decreasing, does show up fairly often on the AP test. To determine whether speed is increasing or decreasing, we need to look at both velocity and acceleration at this certain point. So if velocity and acceleration have the same sign at a given point, speed is increasing. And if velocity and acceleration have opposite signs, speed is decreasing. Particle moving right or up in some cases, velocity is positive. Particle is moving left or down, velocity is negative. And a particle changes direction or is stopped whenever the velocity is equal to 0. Okay, those are the collection of big ideas of velocity, all right, with particle motion. So let's take a look at one random example question. It's the velocity of a particle moving on a line at time t is 5t to the 2/3 power plus 6t. How many meters did the particle travel from t equals 1 to 8?
Wait. So we're looking for total distance?
Yes. How many meters would be total distance?
So we're taking the total from 1 to 8 from the absolute value of the particle.
Exactly. 16. Okay, and we're assuming that whenever we're asked to do an absolute value like this, that it's a calculator question. So what would I get if I plug this into the calculator? Math and over 1 should be the first option.
$282.
Thank you.
282
282.
meters.
Yes.
I can grab you. You want to glaze?
So next week, when we do free response questions, we'll talk a lot more about particle motion because that is a very common type of free response question. Right? But there will certainly be a few multiple choice questions attached to this here. So the next idea we went into was slope fields and differential equations. So a slope field is just a visual representation of all the possible solutions to a differential equation. Right? It just shows a family of functions that take plus c into account. So generally for a slope field, we'll either be asked to match a slope field to its differential equation or asked to sketch a slope field if it's a free response type of question. So we talked about a few strategies to determine a correct differential equation. Okay? One was to look for domain or range restrictions. Okay? These are kind of a dead giveaway. For example, if our differential equation is dy dx equals the natural log of x, well, we know that natural log, we can't take the natural log of any negative numbers. Therefore, on a slope field, nothing to the left of the y-axis would have a slope. Right? So here's an example of that. Right? This would be a slope field of the natural log of x. We also want to look for places where dy dx would equal 0. Okay? Those are also a pretty dead giveaway. Right? So again, on this example here of natural log of x, at 1, the slope is 0, everywhere, okay? Because the natural log of 1 is equal to 0. If the derivative is only in terms of x, then all slopes will be the same horizontally. And if dy dx is only in terms of y, then all slopes will be the same vertically. So the last and probably the most common way of figuring out what slope field matches up with what is just plug in points to see if it matches up with the picture that you're given. Okay, so let's sketch a slope field, and then let's do an example where we have to match a slope field with the correct differential equation. So, too far. So here we're given this differential equation, and we just want to sketch the slope field at the 9 points on the graph. So what we're doing is we're saying, well, I'm taking x to be -1, y to be 2. So if I plug those values in, I mean, we don't have to write all this out every time, but what we're doing, -1, 2, so I'm plugging in -1 for x, so 1 minus 2 over -1 squared, times 2 minus 1. So that would get me 1 minus 2 over 1, so -1 times 1 equals -1. So what? I don't know. I've never gone to try for it. The one on Tusk hasn't tried.
Yeah, that's what I would.
So, but I've never gone through the. So what this means is at the point -1, 2, we have a slope of -1. So I would sketch in a little line here that has a slope of approximately -1. We want to go through that same process for all of the points listed here. Hopefully, we could recognize a few patterns to where we're not doing all of this work 9 times. Okay, one is that, well, I've got y minus 1 as one of my factors. Whenever y equals 1, this will be 0, right? And all 0 times, doesn't matter what this is, because 0 times anything is 0. So whenever y equals 1, the slope would be 0, right? So that would be at all 3 of these points. I will have a slope of 0. It does turn out that we would have to plug in the rest of these coordinate points, okay, and they will be non-zero slopes.
This is one of those things that there's going to be like one question on the AP that's about slope fields. Do you know what I mean?
Probably, yeah. Sure. I mean, if I had to guess, I would say there will be one multiple choice question, and this was part of a free response question, and this is actually a fairly common type of free response question where you sketch the slope field and then you solve the differential equation after that. So if we continue to plug in the rest of these coordinate points, we get -1 again over here. We get about +1/2 here, +1 down here, +1 again, and -1/2. Okay, so sketching our slope field would look something like this. Okay, and just to make sure that we're paying attention, okay, they only asked us to sketch at the 9 points given. They did not ask us to sketch a slope field at these 3 points here. So you do have to pay attention and make sure that you're only sketching the slope field where they ask you to sketch it. And there may be points on the graph where you're not supposed to sketch a slope field. Okay. We okay with sketching a slope field? Okay, we're just plugging coordinate points into a derivative and then sketching out that slope. Okay, so now let's take a look at one where we have to, oops, that's not what I wanted, where we have to match a slope field with the given differential equation. So, we want to think about our strategies here, figuring out which set of slopes matches which equation. Right off the bat, I see right through here, whenever y is equal to 1, we have a slope of 0. What's that? Okay, so whenever y equals 1, we have a slope of 0. So it could be, well, so it may help if we rewrite these so that we separate x's and y's. So if I factor out an x, this would be the same as x times y minus 1. And this would be x times y plus 1. Okay, so whenever y is equal to 1, dy dx equals 0. So, well, this one would work. And if y is 1, dy dx would be 0. This one would work. And this one would work. So we can eliminate b and c from that piece of information, right?
Wait, E doesn't work. E does work.
Well, so e is only in terms of y, right? There are no x's in that equation. So if our answer were e, we would have to have the same slope all the way across for every y coordinate.
So it's not.
So we can eliminate e as well. So now we're just down to a and d. So let's just pick a few points and plug them in and see what happens. It doesn't really matter where we start. We can say, well, at 1, negative 1, it appears that we have a slope of about negative 1. So if I plug in 1 for x, negative 1 for y, let's see. Here we would have 1 times negative 2. Here we would have 1 times negative 2. Well, that doesn't really help us. So let's go into the negatives. Let's say at negative 1, negative 1. Looks like we have a slope of approximately, I don't know, positive 1, positive 2, something like that. So if I plug negative 1 in here, negative 1 times negative 2 would be a positive 2. Here, negative 1 squared would be positive 1 times negative 2 would be a negative slope. But it's positive. Okay. Does that make sense? Okay, so using our strategies, we can eliminate a few answers and then just plug coordinate points into our remaining possibilities to figure out an answer.
Because if you plug in negative 1, this one equation is x times y minus 1, right?
Yes.
If you plug in negative 1 for x and y, you get 2 times negative 1.
You get negative 2 times negative 1. We okay with that one? Alright, so right after slope fields then, we talked about solving differential equations. So this is just given a dy dx, right? Given an equation like this, we want to solve this. We want to anti-differentiate. So the first step to solving something like this is to separate variables. I want to get all my y's and dy's on one side, and all my x's and dx's on the other side. Okay, so this problem here, finding the particular solution to this differential equation, this was worth 6 points on a free response question. Okay, sketching the slope field, which we just did, was worth 2 points. And then there was another, part A was some random thing. There was only 1 point, I don't remember what it was. But then this part C, to solve the differential equation, was 6 points. So to solve something like this, I'm going to divide my y minus 1 over and multiply my dx. So I will end up with dy over y minus 1 equals 1 minus, and I'm going to go ahead and rewrite this as 2x to the negative second. So once I have my variables separated, then I can take the integral of both sides. So I need the antiderivative. What's the antiderivative of dy over y minus 1? It is the natural log. Whenever I have the derivative over a function, that antiderivative is natural log. So this would be the natural log of y minus 1. Then over here, antiderivative of 1 is x. How about the antiderivative of negative 2x to the negative second?
Positive. Wait, positive.
So we add 1 to the exponent. So negative 2 plus 1 would be,
And then you divide by the new exponent, so it's going to be that.
positive 2. Okay. And then don't forget your plus c. Now, we're given an initial condition, okay, the point 1, 2. So we want to plug 1 in for x, 2 in for y, and solve for c. Technically, it doesn't matter which side we put it on. It's just right. It's just customary to put it on the side with the x's. So plug in 1 for x and 2 for y. We'll get natural log of 2 minus 1 equals 1 plus 2 times 1 to the negative first plus c. So this is natural log of 1. What's the natural log of 1?
0.
0 equals 1 plus 2 times 1. This would be 2. So we get 0 equals 3 plus c. Subtract the 3 over, and we get that c is equal to negative 3. Okay. Now, I want to take that value, plug it in for c up here, and solve for y. So I'm just going to rewrite this. Natural log of y minus 1 equals x plus 2x to the negative first minus 3. So how would I solve this for y now?
You don't. Well, we can do the
Do the e thing.
E thing.
Yeah, whenever we're taking a log, to undo a log, I would raise both sides to a power of the base. Right? So the base of a natural log is e. So I'm going to raise both sides to the power of e. So e to the natural log cancels out. So this side just becomes y minus 1. And we have e to the x plus 2x to the negative first minus 3. Add 1 over. We're done. 6 points. Right there.
Oh, by the way, Monday we can do a lot of dinner. And Tuesday.
They'll get to review the AP Calc test.
I'll be here Monday. Will you be gone then?
Questions on differential equations?
I won't be here Thursday.
Not Wednesday.
I'll be here Tuesday.
I will be.
We're all just disappearing from your class.
Don't follow me for the next like 7 days.
What?
That's
I can't.
That's pretty much time we have until the AP says.
I don't count the AP test. Because we have 4 days next week, and then the following week we only have 4 days for the AP test. Well, for special Olympics.
The
So
actual,
you guys have 7 with. I have.
the only school day I have next
There's
week
not
is
enough time.
Wednesday.
To get my life together in 7 days.
We
You got plenty of time.
Not letting my book really.
I don't. Okay, let's continue.
All right, next idea, average value. The average value of a function is just the integral of the function times 1 over the difference between your bounds, 1 over b minus a. So make sure that you don't confuse this with average rate of change. Average rate of change is the slope between 2 points. Average value we get using this integral. So here's an example given a graph. And it says we want to find the average value of this function on the interval 0 to 8. And we're given that these areas are 14,
16.
16, 15. So average value would be 1 over 8 times the integral from 0 to 8 of f of x dx. Right? Well, instead of finding an antiderivative, okay, we're just given the area under the curve. And remember, an integral just means area under the curve. So this would become 1/8 times 14 minus 16 plus 50. Right? The 16 is negative because that's area below the x-axis. So we just get 1/8 times -2 plus 50 is 48. So 1/8 times 48 is 6. Questions on average value? All right. Then next, area between 2 curves. So, to find area between 2 curves, it's always a good idea to try to sketch out a picture. Even if you don't know exactly what the picture looks like, having some kind of picture is helpful. Did I skip one?
Yeah.
Oh, I did, didn't I? Let f be the function defined by 1 over x. What's the average value on the interval 4 to 6? So average value, we're just setting up our integral from 4 to 6 times 1 over 6 minus 4 of 1 over x dx. So what's the antiderivative of 1 over x?
Natural log.
Natural log. Right? So this would be 1/2 times the natural log of x evaluated from 4 to 6. So 1/2 times the natural log of 6 minus 1/2 times the natural log of 4. How can I combine logs if I'm subtracting them? Divide what's on the inside. And so this would be the same as 1/2 times the natural log of 6 over 4. 6 over 4 reduces to 3 over 2. And that's why that's another answer choice. They are very, very good with distractors. We okay with average value? All right. Now area between 2 curves. So to find area between 2 curves, I just want to take the integral of the top curve minus the bottom curve between where they intersect. So we have to find those pieces of information. I have to find where they intersect. So if we're looking at this example, find the area between f of x equals x and g of x equals x squared. I first need to find the bounds, or where these two functions intersect. So to do that, I set them equal. Say x equals x squared. To solve this, I'm probably going to want to subtract my x over. I can take out an x, and then I get x equals 0 and x equals 1. So those are my bounds. Those are the places where these two curves intersect. Okay? Now I want to figure out which function is greater on that interval between 0 and 1. Yeah, plug in a half. Plug in a value in between 0 and 1. So if I plug in a half here, I get a half. If I plug in a half here, I get a fourth. So x is greater than x squared between 0 and 1. So what we have then is something that looks like this. So we're finding the area of this region. To do that, we're just setting up this integral. Integral from 0 to 1 of the top function minus the bottom function. So x minus x squared dx. To do this by hand, just taking the antiderivative of each piece. So 1/2 x squared minus 1/3 x cubed between 0 and 1. So plug in 1. 1/2 times 1 squared minus 1/3 times 1 cubed minus, if I plug in 0 to both of those, I'll just get 0. So I end up with 1/2 minus 1/3. Technically, if this were a free response, we could stop back here, right? But something like this would probably be a multiple choice question, so we would want to finish this, so we would need common denominators. We would get 1/6. Questions on area between two curves. It's just top curve minus bottom curve between where they intersect. Alright, then the final idea is volume. Okay, we talked about a few different situations with volume. The first was volume if we're told what the cross sections are, okay, or volume of known cross sections. So the big idea is we want to write some function that gives us the area of the cross section, and then we want to integrate that. So for this example here, squared kind of got cut off there. We are given this function, okay, y equals negative x squared over 9 plus 4, and y equals 0. So this is the region that we're looking at, and cross sections coming out of the board are rectangles with heights that are twice that of the side of the xy plane. So what it's saying is, here's the base, the height coming out of the board is twice that length. So my rectangle is twice as tall as it is wide. So we need to come up with a way to express this width, okay, the base of the rectangle. Okay, well, that height, or that length of the base, is just going to be top curve minus bottom curve. Right? So it's just going to be negative x squared over 9 plus 4 minus 0. So it's just negative x squared over 9 plus 4. The other side is just that multiplied by 2. So to write an area function for this rectangle, just multiplying base times height, right? So I would just end up with 2 times negative x squared over 9 plus 4 squared. Now to find the volume, I integrate my area function. 2 times negative x squared over 9 plus 4 squared dx. I still need my bounds. What would my bounds be? Yeah, so from the graph, we can see it's negative 6 and 6. If I didn't have a graph, how would I figure that out?
Well, both of them equal 0.
Yeah, set negative x squared over 9 plus 4 equal to 0. Solve. So I would subtract 4, multiply by negative 9, we get x squared equals 36. We would get negative 6 and positive 6. So this is one we could do by hand. Okay? To do by hand, we would probably want to square this out. Okay? Multiply everything out and then take the antiderivative of each piece individually. But for time's sake, use a calculator here. And I think we get 204.8. Questions on volume of known cross sections? The final idea then is volume of revolution. So here, I want to take some region and revolve it about a horizontal or vertical line. So here, we're given this region enclosed by this function and the line x equals 1. So the first part says find the volume if this region is rotated about the x-axis. My goal is still to write an area of a cross-section function. So I'm thinking if I revolve this about the x-axis, well, the area is going to be a circle. So I'm going to say my a of x here is going to be pi times the radius squared. Okay, well, the radius is going to be the distance from the function to the axis of revolution. And that's just this function. Right? So pi times e to the 2x squared, pi times the radius squared. And I could simplify this. I could say this is just pi times, if I'm raising a power to a power, I multiply them. Right? So e to the 2x squared would just be e to the 4x. To find the volume then, I integrate my area function. So the volume will be, I can pull my pi out front. So there's the integral of e to the 4x dx. What's that? And my bounds would be 0 and 1. Yes. All right, so we could actually do this one by hand fairly easily as well. Okay, we want to think about the antiderivative of e to the 4x. Technically, this would be a u substitution problem. Okay, but we may be able to think about this without doing a u substitution. If I take the derivative of e to the 4x, that would be e to the 4x times 4, right? So if I think about going backwards, okay, if I got e to the 4x as my derivative, what coefficient would I need out front to make the derivative just be a 1? 4. Right? So if I'm taking the derivative, I would have a 4 out front. If I take the antiderivative, I would have a 1/4.
Don't look at me, I don't know.
I mean, watching things.
Well, you
didn't
won't
either.
At least I should. I've been paying attention the entire time. I just want to answer.
So if we think about a quick u substitution, if u is 4x, du would be 4. I want it to be 1, so I would need to multiply both sides by 1/4. Okay? And that's perfectly fine. Yes, it is.
I'm taking.
No. Shut up.
I was gonna put take. You didn't spell it. No, because I was thinking in my head, I was gonna say that I'm taking.
taking. I was spelled taking, but my mouth wanted to spell take.
My mouth.
My mouth and my
How do you have any faith in us? To me? To who? E to the 0 just for me.
E to the 0 is 1. Yes.
Okay.
Alright,
That's done.
that's done.
I thought
Final.
you said done.
Final problem. Let's take this same region and revolve it about the line x equals 2 and find the volume. I think so. So now we are taking this vertical line. And I'm going to take this region and revolve it about this line. If I do that,
Oh my god, that is
is this what? Yes. So here we'll have to do big R and little r. If I revolve this, I will have a circle with a hole in it as my cross section. So we need to think about big R and little r. So little r would be this distance. Big R would be this distance. Right? So I'm doing pi times big R squared minus pi times little r squared. So the distance between 2 and 1 would just be 2 minus 1. Right? So my little r is going to be 1. My big R is going to be 2 minus my function. Whenever we are revolving about a vertical line, I need my function as x equals, and then in terms of y. So if this is y equals e to the 2x, to solve this for x, I would take the natural log of both sides, and then divide by 2. So we get the natural log of y over 2 equals x. So my big R is 2 minus the natural log of y over 2.
Put these in now.
So my area function then is pi times 2 minus natural log of y over 2 squared minus pi times 1 squared. Sure.
Just for a second, the spell's coming off those.
So the volume then is the integral of this area function.
Why are you complaining? We're never paying attention. What you said? You were never paying attention. She wasn't I know, that's what I'm saying. I had to ignore the whole class.
She acts like she's over.
She acts like she's upset. Because
Okay,
she's actually trying to do
bounds.
this.
What would my bounds be?
0 and 2. POS.
0 and e squared.
Oh no!
We're looking at the y value here. My bounds would be 0 and e squared. This then we can plug into the calculator and get 34.820.
We got close.
Good thing I
Or not.
Alright, take a look at these multiple choice questions tonight over the weekend.